University of Oxford Astronomy. Dr. Meg Urry was president of the American Astronomical Society. She worked on the staff.
Slightly bigger than yours.
Yeah, a little bit. You wouldn't know it today. She worked on the Hubble Telescope staff and was chair of the Department of Physics at Yale. So she's been busy. Dr. Meg Urry.
Yay! Wow, this is really fun for me to be so close to such a big crowd. But you have to leave unless you can read this. Pretty good. I have a translation. Black holes in the evolving universe, and the point of having this as a title is to point out that there are so many different kind of galaxies in the universe that you can actually make an alphabet. And this was done by the Galaxies crowd, which I'm going to talk about at the end of the talk. If you're interested, you go to writing.galaxieszoo.org, and you can type in anything, your name, your friend's name, anything you like, and it will galaxify it. It is kind of cool. Dan, were you like turning out lights before? It would be good if
you want me to? Sure.
Yeah, like a little bit of.
We were doing it randomly just to see if anybody knows.
How
about this one?
It's okay with me, but I don't know if people are. But no snoring.
That's good.
Yeah, that's good. That's good. Okay, so let me start by saying that there's a really wide variety of galaxies. I feel like I brought my coals to Newcastle here. You guys know so much more about Messier objects than I ever did. So, okay, but maybe some of you don't. So I'll start there. So this is just a montage of a lot of different kinds of galaxies. And I want to point out some of the different features. So if you look at this upper right, this is a galaxy kind of like our own. It's got a disk, it's got spiral arms. Our Milky Way probably looks like this. We don't have a picture of our Milky Way because we're in it. So it's a little hard to go do nice photographs, but from various measurements, we think that's what it looks like. Down here is a galaxy. It's called an elliptical. It's much rounder. Probably this galaxy resulted from the merger of two roughly equal mass disk galaxies. So we think that's where these kind of round galaxies come from. The one in the middle with this huge bulge, it has a bit of a disk, but probably it's had many, many interactions and many mergers, and that helps fluff up the stars, the orbits of the stars, and makes this big bulge. So the point is we can study all these galaxies and see that they're different. The colors are also significant. The redder ones have older stars. The bluer ones have newly forming stars. And you see in the upper left a picture. It's actually similar to one of the ones that you just showed, which is two galaxies that are passing near each other, distorting each other, and probably will merge sometime soon. So we use these as clues to the history of the galaxy and actually in some cases its future. But my talk is about the black holes that we have known now for a couple decades are hosted at the centers of nearly every galaxy above a certain mass. And for the youngsters, this is old hat. I mean, there's a black hole in every galaxy. The kids, if you've been through 4th grade, you probably already knew this and you're thinking, what's big about that? But when I was younger, we thought black holes were very rare and they were only in occasional galaxies. And most galaxies didn't have them. So that's a really huge paradigm shift that happened around the year 2000. And how did we know there were black holes in galaxies? There are a lot of different lines of evidence. I won't go through all of them. Some of them came from Hubble imaging and looking at the light distribution and modeling the stellar orbits. But here's one set of observations that I really like. This is a movie put together by Andrea Ghez, who's a professor at UCLA and very famous for having accurately measured the mass of the black hole at the center of our galaxy. What you're looking at is the orbits of stars in the center of the galaxy that she has measured over the last 20 years, more than 20 years. Andrea was an undergraduate at MIT when I was a postdoc there, so we are old friends. I've known her for many years. But anyway, mapping these stars is a way of weighing the mass interior to their orbit, or in other words, the mass of the black hole at the center of the galaxy. I'm going to come back to this picture and tell you more about it, but because I'm a professor of physics, I'm going to give you the physics of it first. How many of you have had physics? Some of you are physicists. That counts too. Okay, so Newton told us that F equals ma. The gravitational force on an object is equal to the mass of that object times its acceleration. So if you have something going around another mass, like for example the Earth circling the sun, okay, the Earth is orbiting the sun because of the gravitational force of the sun on the Earth, and it's accelerating. Accelerating means changing its velocity constantly. So you can use this, and in first year physics, we do use this to figure out the mass of the central object. So let me just show you how you do that. First of all, there's Newton's law of gravity that says that the force between, say, a black hole of mass big M and a star of mass little m is proportional to the product of their masses divided by the distance between them. So I'm calling R star the radius of the circular orbit that a star or planet is making around the central mass, say around the black hole. But you could imagine this to be the sun and the Earth and the radius of the Earth's orbit. And then G is just Newton's constant, proportionality constant. Well, that has to be equal to the mass of the star times its centripetal acceleration, which is its speed squared divided by the radius of its orbit. And this is a very simple, algebra to do. It turns out the mass of the orbiting object disappears. You don't care what its mass is. But if you can measure its velocity and the radius of its orbit, you have measured the mass of the object that is holding it in orbit. So that's how we know how much the sun weighs, right? We didn't go out with a scale and put the sun on it. We watched the orbit of the planets around the sun, and that tells you the mass of the sun. It's a little more complicated because the orbits aren't circular and so on, but if you can watch something moving, you can see what the mass of the central object is. You with me? So let's go back to the black hole. Here's the black hole. There is a black hole at the center of our galaxy. Again, this is not something we knew way back when. Andrea and another group, Reinhard Genzel's group in Germany, have both been monitoring these stars. These are stars very, very close to the center of the galaxy. And I want you to notice that the stars in the center part are moving much faster. I'm going to make you go back and learn the physics lesson. Hang on. So if the mass of the black hole is just a thing, it's like, in fact, in our galaxy, it's 4 billion times the mass of the sun. Okay, it's a fixed mass. So if you're closer in, if R is small, you have to be moving faster. V has to be higher. You see that? Because it goes as V squared R. So watch, what happens when you watch the stars orbiting, the ones in the center are going really fast. And there's this one super duper star that you'll see that comes in on a highly elliptical orbit. And when it gets close, it just whips around that black hole and heads back out. And that star was the one that Andrea discovered. Reinhardt's group didn't even see it until after she published it. Here it comes, that one. Okay? And those things, you can see that they circumscribe a small volume. So what these data prove is that there's a huge mass inside a very small volume. And it turns out that a black hole is about the least exotic explanation for the orbits of these stars. So this is the best evidence in the universe for the existence of a supermassive black hole. And it's at the center of our galaxy. Now, that's ours is a very dull black hole. It's a low mass. It's not that massive. I mean, a few millions, nothing. I study ones that have billions of solar masses. Our black hole is also very dormant. There's very little matter falling into it. And we are all grateful for that. Because if there were more matter falling into it, it would release more energy, not from inside the black hole, but from the environment. And some of that energy would be gamma rays, and Xrays, which can, could evaporate our atmosphere or something unpleasant. So we like dormant black holes to live near, and we like active black holes to study. Here's an active black hole. This is just an image of the center of M87, another Messier object. This one actually no. And this is an early result from the Hubble Space Telescope. Gosh, it must have been in early 1990s. Some of you weren't born yet. And the cool thing about this was not only did they image a disk at the center of M87, but they were able to measure with a spectrograph the velocity of the gas. Can you see those two circles superimposed on the disk? Those are the locations of the light intake for the spectrographs. And what this cartoon is supposed to show you, that one of them is blue shifted and one of them is red shifted. That disk is rotating. And again, just like the stars going around the black hole, if something's moving and you can measure how fast and where it is, which you can from that image, you've weighed the black hole. Now in this case, this is about 1 billion solar masses, the black hole in this particular galaxy. And this galaxy, some of you will know, I don't have the image, but it has a huge jet that spews out one side. I wanted to, this cartoon, it's just an artist's picture. This is to remind me that I talk about black holes giving off a lot of light. Of course, we all know they don't give off any light, that no light can escape from inside a black hole. But the region around the black hole can be very, very bright indeed. And so when black holes at the centers of galaxies when a lot of matter is falling into them, the conversion of that gravitational potential energy, it's converted, some of it's converted into light, and they shine very brightly. So it's kind of like, you know, if I drop something, it gains energy, and that energy can be converted to light as it goes through, say, an accretion disk or in the vicinity of magnetic field. So that's what that cartoon is supposed to remind me to say. Let me show you a few examples of, well, here's Cygnus A. This is a radio galaxy. And this is the object. This is an iconic object that was sort of the first best argument for the existence, for the idea that black holes powered phenomena in the centers of galaxies. What you're looking at is an image taken in radio light, so that, you know, like a satellite dish, like DirecTV kind of satellite dish. If the optical galaxy were on here, it would be about this big. Okay, it's a small sort of, it's near where that point of light is, but a little bit bigger. These, there are two jets coming out that are highly collimated. You can see one here pretty clearly. I think if you squint and you're near the front, you can see one on the other side. That's because this particular galaxy is nearly in the plane of the sky, so the two jets are of similar brightness. If they're tilted more, so that one of them is pointed at you and one's pointed away, there's a special relativistic effect that makes the oncoming jet very, very bright and the receding jet very dim. So usually when we see these collimated jets, they're one-sided, and it's just special relativity. Einstein's theory from 1905. This tells you that something violent is happening in the center of this galaxy. And Ronald Lyndon Bell in 1969 made a cogent argument that if you count up all the energy that has to power this enormous radio source, it's a huge amount of energy. And he had another argument for it needing to be produced in a compact region in the center of the galaxy, stemming from variability. And when you put those two things together, you basically, and you ask that the energy ultimately comes from gravitational potential energy, you essentially are forced into thinking this is powered by a black hole. At the time, 1969, I mean, I didn't know any astronomy then. I was alive, but I was small. But people thought black holes were just far too exotic to be true. But he showed that they were sort of required in this case. Here's another nice image of what we call an active galactic nucleus, or AGN. This one's called Centaurus A. I guess the label isn't on here saying it's Centaurus A, or Cen-A for short. And what you're looking at is a multicolored image where the light from different wavelengths is added together. So for example, if you look down here, these are the different wavelengths. So look at this green image here. This is the radio image that shows jets, just like the Cygnus A image I showed you before. But now I've added on top of it the optical stars image with a dust lane across the middle. And in the blue, you see X-rays, which come from a variety of sources. And then in a different wavelength, this is hydrogen. This is the wavelength of hydrogen. You see the disk of the galaxy and the dust. So when you put it all together, the key thing is these jets coming out are kind of the signpost saying you've got a big black hole. Okay. So I decided I should give you the history of the universe in one slide. Here it is. It's a cartoon. Some of you will recognize this as the WMAP cartoon. It's showing time going from the left, from the Big Bang and the period of inflation to the present day. The very, very beginning was very violent, and in an extremely short period of time, 10 to the minus 33 seconds or so, the universe went from something the size of this, smaller than a nucleus, to something the size of this room, a factor of 10 to the 60 increase or bigger. That's called inflation. And then after that, it was kind of coasting. And the slight bell-shaped curve, the real experts among you will recognize this is a sort of a cartoon version of how originally the universe expansion was slowing, and then in the present day it's accelerating, it's flaring, it's going faster. And that's a marker for this mysterious new quantity, dark energy, that we don't know what it is. But situated in this timeline of 13.7 billion years, the idea is that early on, the first stars formed, maybe a few 100 million years after the Big Bang. They were unusually large because they were made out of pristine hydrogen plus helium and not much else. And they lived a very short time and exploded and left behind black holes at the densest points in the universe, so where the density was slightly higher than average. And that's the natural location for, over time, for galaxies to grow. So the galaxy grows around where this seed black hole was left. That black hole was probably 100, maybe a few hundred solar masses. And today we see that even a wimpy one like our galaxy is 1 million. So they had to grow. And they grew by material falling into the black hole. So they increased by many, many times their own mass by accreting matter from the galaxy around them. Questions? Yeah.
How does a black hole stop getting mass into it? You said our
Yes,
black hole
ours is dormant and some of them are not. So we don't know for sure. If you calculate how much stuff would just fall in randomly given the density of matter around most galaxies, it's not a lot. So for the ones that are accreting a great deal, like Cygnus A or Centaurus A, the examples I showed you, they're accreting at a much higher rate, like a factor of 100 million more than our galaxy. It could be any number of things, but one idea, which I'll come back to, is that two galaxies that are passing each other and perhaps merging, they exert a force on one another that is a tidal force, a torque. So that could funnel matter down into the center. So mergers are thought to trigger the growth of black holes. And in some cases, they may. That's a very popular theory. So now you're going to become the super experts. If you go out and tell the average astronomer that's what you learned, they will believe you are correct. And my group is basically partly showed that that isn't actually working for most galaxies. So just so there, that's like the hyper news.
So what is your theory?
Well, I don't have I'm just out there trying to see what is. And one of the ways we can look at the reason I was talking about shapes of galaxies, we can look at the shapes of galaxies and figure out whether they had a merger recently. And then we can look at all the active galaxies we know and say, okay, do they all look like they had mergers recently? And the answer is no, most of them do not. A few of them do. And particularly the more luminous ones, yes, they look like they just had a big merger. So that probably triggers some, but it's like less than 20% locally. And maybe still less than half at the peak of black hole growth. So it doesn't work for most galaxies.
So you're saying even though galaxies in general have black holes, that some haven't gone through a merger, so that idea doesn't hold water?
The ones that are rapidly growing, that we can see rapidly growing, have not, for the most part, have not had a recent major merger that would have triggered that growth. Yeah. I mean, most galaxies have merged at least once. Many galaxies have merged many times. So there are mergers, but they don't seem particularly connected to the growth spurt of the black hole. Now here, let me give you another sophisticated thought. It may be that the black hole growth phase is very short, and the way the stars evolve is very long. So it may be that we're sort of looking, when we look at the black holes that are growing, we're actually looking at random times in the history of the galaxy that don't mark well the mergers. The mergers take hundreds of millions of years. Suppose the active growth period is a few thousand. Then you could decouple the causality. That may be another explanation. I'm trying to be fair to all these
Could
ideas.
it be that what's happening within that galaxy too, the speed of things
Let me
happening?
pause this a second. Say that again?
Could it be the speed of things happening in the galaxy itself?
So the galaxy, no, because the way the stars move, the way they age, that stuff is all super slow. It's just physics. It's just really slow. The only thing that's fast is down in the very center on very small scales where this black hole is. That's really fast. We can see, for example, the X-rays from one of these galaxies change by large factors in a day, in less than a day. That means huge changes are happening at the center where this black hole, but that's because the scale is very small and maybe a star fell in and then nothing happens for a while and like that. Okay, I'm going to show you a movie now, which is a computer simulation. It's the point of this simulation is to explain how the growth of black holes in the centers of galaxies could have a profound influence on the evolution of the galaxy itself. And that's because as the black hole grows, it releases a lot of energy into the galaxy in the medium, the intergalactic medium. So what you're watching, I'll set it up so you can really appreciate it. This, you can't see it right now, but in the lower left, it's going to give you the time scale since the Big Bang. And we started about half a billion years after the Big Bang. And you're looking at first at blue color, which is the dark matter distribution. So that gets, let me see, let's go again. Hold on. And forward one more time. Sorry, let me just make this start itself again. Okay. So here's the time since the Big Bang, half a billion years. The density is given in blue, and the dense parts just keep getting denser over time as gravity pulls matter toward the denser parts, and then the emptier parts get emptier. So what you're looking at is a web, a cosmic web of matter that develops over time.
How big is it?
Pardon?
How big is it?
This is, that's a really good question. It's about between 10 and 100 megaparsecs co-moving, and I've forgotten.
Those are galaxies.
Those are galaxies and clusters of galaxies.
Clusters of galaxies.
Yeah. The big things are big clusters of galaxies. Okay, now when you see the color change, what you're looking at now is temperature of the gas in the galaxies. Okay, so not dark matter anymore. But now you see these explosions. You see that huge explosion? That was a period of black hole growth. There's another one. You also see some little flickers. Can you see those in a couple of places? Those are supernova explosions, which also release energy into the galaxy. Both kinds of explosions drive matter out. Now they're actually, which is good, because after the stars have made heavy elements, you need to disperse them in order to get them out there so that the Earth can form and we can form, because we're made of atoms that are not just hydrogen and helium, and those had to be formed in stars. Okay, the purple color this is chemical abundance. So this shows you white is more heavy elements, black is hydrogen and helium, so you're seeing that the purple is kind of this intermediate chemical abundance, and that stuff is being spread out across the universe through black hole growth and supernova explosions. So, of course, they aren't really explosions. I mean, supernovae are, but the black hole growth takes place over long periods of time. And in this simulation, they don't put in a time scale. They have a kind of a fake time scale. And so, in fact, what you saw probably happened over 100 million years or so. So when you see it, one of those big bombs, that was 100 million years going by quickly. Anyway, it's a fantastic simulation. and it's an illustration of how you can imagine the galaxies that host black holes being affected by their growth. Now, somebody asked about mergers, so I also brought a movie. This is another computer simulation that shows you what happens at much higher resolution than the last movie when two disky galaxies merge. And what I like about this particular simulation is that they stop it every so often and show you an actual pair of galaxies that has been observed on the sky, showing you that, we see all these different stages of mergers. There's an example where two galaxies are about to merge. And then as the merger continues, you see these vast tidal tails that are being spun out. That's because those occur because the near sides of the galaxy pull more on each other than the far sides, which has the effect of stretching each galaxy out. And so when you see these kind of tails, you know you're at a particular stage of a galaxy merger. Anyone recognize what this one is? This is the antenna galaxy. I think there's one more of these. Eventually these tidal tails disappear because the stars are so far apart that you no longer see. I'm sorry, this is the antenna. Did I over? Yeah. You cease to see you cease seeing the tidal tails fairly soon after the merger takes place. But we see mergers in all stages. So here's a montage of pairs of galaxies at different stages of mergers. The total merger of those two disk galaxies takes hundreds of millions of years. So what we see is we don't see anything move. We just see, like if you look at this guy, it's hard to see from this angle. I think this is ARP220. This is nearly merged, okay? And you see this one has barely begun. So you see lots of different stages of these mergers. Okay, so let me just say about 2 words about my own research. What I've been working on lately is surveys to take a census of when and where black holes are growing and to model that growth theoretically. So we use the Hubble Space Telescope. Probably you recognize it. The real cognoscenti in the audience know this picture was taken probably 25 years ago. How do I know that? Anybody got an idea? Like how you know that's a really old picture of Hubble?
The shuttle was next to it.
Oh, well, there is that. The shuttle was next to it. That's
Solar panels?
solar panels. The solar panels are bent. Those are the ones that didn't work very well, that they got rid of, I think, within a few years. I think 3 years after launch. So anyway, the new solar panels are nice and straight. We also use the Chandra Xray Observatory and the Spitzer Space Telescope. Those are both of these are drawings because we didn't have a shuttle up to take pictures of them. And the fortunate among us get to go to Hawaii to go observing with the Keck Telescopes. You're looking, the 2 white domes are the 10-meter twin Keck Telescopes, and right behind the one on the left is the Subaru 8-meter telescope. Observing from Hawaii is very posh because you don't go up to the mountain where there's no oxygen and you can be too stupid and break things. You observe from 3,000 feet at the headquarters in Waimea. And so it's really cushy. I mean, yeah. None of this out in the cold with your down jacket on, as it was when I started, I have to say. This is a mock-up of the Keck Telescope, which is has 36 segments that are about 3.5 feet across. So, but you can see how big each telescope is by looking at those people. And this is the summit of Mauna Kea. Again, you see the Keck Telescopes sort of to the right over here, Subaru, and then a bunch of other telescopes up there. And TMT will be, if it's built on the mountain, will be back here on the backside.
Didn't it just get a go-ahead to start that again?
The permit was just approved, yeah. And I think the consortium has to decide they're going to go forward, and I think they're trying to make sure there's nothing that's going to get in their way again. Yeah. So, so a big project I did actually a few years ago was called GOODS, the Great Observatory's Origins Deep Survey. It was the largest, deepest survey of the sky at the time, and it used what NASA called its great observatories, which were Hubble, Chandra, and Spitzer. So hence the acronym. Although we added Origins because we didn't add another letter. That looked a bit arrogant, I think. But anyway, the image you're looking at behind that is actually one of the good images, really deep image. Here's a blow up of a tiny part of it. For this, just turn off the lights just for this.
Sure.
This picture is so great. I don't know if you can see it. What you're looking at are very faint, very distant galaxies. And then the three circles are showing you where the X-ray sources are on this image. This image is an optical image, but emitting X-rays are from these three places, which are three galaxies, two of which you can see here and one of which you can't. And X-rays are a really good marker for rapidly growing black holes. They produce very high energy radiation, short wavelength X-rays. So these are three AGN candidates. They are all AGN rapidly growing black holes. And to make a long story short, the yellow circles are showing you the ones that are hard to see in the optical that we discovered in X-rays. And you can find them in the infrared too. Here's an infrared image superposed showing that that those things are emitting a lot of light as well. So are a bunch of galaxies. I mean, for our purposes, galaxies are kind of nuisance objects in the field. But this was our first chance to model the growth of black holes. And I'll just give you the sort of bottom line. We found that, as others had found previously, there's a big black hole growth spurt in the early universe from about 5 billion to 10 billion years after the Big Bang. Many of them are hard to see at optical wavelengths, which was the usual way of looking for them. So, in fact, previous surveys had missed 3/4 of the growing black holes, and our survey found them. And then, I won't talk too much about it, but mergers are probably not, I did say mergers aren't important in most galaxies. So let me go back to talking about galaxies, and this is the last little topic I want to talk about. You know, I came from the physics area, and so when one of my postdocs told me he was going to look at galaxy morphology, you know, shapes and of galaxies, I just kind of yawned, like, who cares, you know? Those are big scale things, and the black hole's down the middle. How would the black hole even know what galaxy they're sitting in? But that was how stupid I was. I had forgotten that the shape really encodes the merger history, and that is a very important thing to study. So my postdoc, Kevin Shawinski, he was actually the co-founder of Galaxy Zoo. How many of you have tried Galaxy Zoo? Okay, just a few of you. Good. I'll tell you a little bit more about it then. So Kevin and his friend Chris Lintott were postdocs at Oxford. And Kevin was, well, actually he was a graduate student. Kevin was a graduate student. He was working on his PhD thesis. You can turn the lights back on, by the way, because I think I don't have too many dark things anymore. Anyway, so Kevin, for his PhD, he classified by eye 50,000 galaxy images. This is what graduate students do, right? They sit at a table with a microscope. And he finished that and he said, oh my God, he said, I'm never doing that again. And not only that, but to do better, you'd have to do like much more, right? You couldn't do another 50,000, that's only a factor of 2. You'd have to do 500,000. So they're sort of scratching their heads in the pub over a beer. And they said, why don't we put these images online and let the public classify them? So they invented Galaxy Zoo, and within a week, one of their software friends had written an interface. This is a screenshot of the interface a couple days ago. Basically, they give you a little tutorial on what you're looking at, and in the beginning, they just asked you, is this a disk galaxy or is it a roundish galaxy? In other words, has it not had a recent major merger, or has it had a recent major merger? That's essentially what they were getting at. They put out a little press release saying, we have this thing, Galaxy Zoo, come see. And they melted the servers at Fermilab. So many people logged in. It was phenomenal. Within a few months, they had 250,000 people classifying galaxies. And what was fantastic about this is instead of one tired, perhaps drunk graduate student saying disk, not disk, you know, like that, you had hundreds of people. So they kept it going until each galaxy had been seen by 100 people and classified by 100 people. So you had a distribution, right? You could say, okay, give me all the ones where 80% of the people agreed. Those are pretty secure classifications. The ones where 50% said that and 50% said that means you can't really tell from this image that we were given. So it was extremely good that way. Also, they did a lot of sociology. They discovered they could weight the observers, the classifiers. There was one guy, we don't know the gender, there was one person who classified all 1 million images. But
That's your postdoc.
But first of all, he was no better than random compared to. So if they looked at the people who agreed, like the galaxies where people really agreed, and they looked at his classification, it was randomly the same or not. Okay? And then they looked at the time interval he used to classify the galaxy, and it was less than a second. So this guy was watching TV and going left, right, this. And sure enough, he did 1 million, but he wasn't even looking at the images probably. So they weighted him 0. Okay? And then they took the people who were really good at it and they weighted them higher. So it was an extremely effective process. So this was the birth, one of the origins, there are others, but really one of the key citizen science projects that started. And this shows you some of what they found. Here on the top row are spheroidal galaxies, on the bottom row are disk galaxies, and they range in color from blue at the left to red at the right. And we use this to show that galaxy evolution really sorts according to morphology. That was the first time that had been done. Kevin did that paper in 2014, so not that long ago. It's a long time for some of you, but for me it's like yesterday. And it was a really interesting result. So these same people, particularly Chris Lintott, created the Zooniverse. Do any of you know about the Zooniverse?
Yeah.
Okay, so the Zooniverse is 100 projects of all different kinds. There are a few astronomy ones. There's one on gravitational lensing. There's
Brown dwarfs.
brown dwarfs. There's a bunch of astronomy ones, but mostly there are other things. So there's animals in the Serengeti, there's biology, and if you feel like doing real science, this is not, it's not letting your computer CPU be used by SETI to decode signals, right, which is a passive. In that case, you're passive. You're letting your computer be used. This is you actually doing science. So it's a great resource. It's a great resource for the scientists, but it also lets people see what research entails. So, okay, now the last 2 minutes here, I want to say something about artificial intelligence. Okay, Galaxy Zoo took people really far, and in the end, they had over 1 million people working on Galaxy Zoo. Over 1 million people were classifying galaxies. But the volume of data was tiny compared to what is coming. So now I have to switch over to my keynote. Hold on. These 4 slides were made by my, let me see if I can do it. Yep. Were made by my student, Aritra Ghosh. Let me go up to the beginning. Oops, I should have gone to the beginning at the beginning. That would have been smarter. Okay, so here is LSST, the Large Synoptic Survey Telescope. This telescope is going to look at about half the sky every night. It's going to create 15 terabytes of data every night. And as many galaxies as Galaxy Zoo processed in a year, they'll get every night, or probably many times that every night. So you can't get enough people to do the work. So how are we going to interpret our data? So the idea is to go to machine learning. So I'm going to say just a couple of words about machine learning. Oh, this is LSST, how it's going to work, taking different filter images. I should have said, this telescope is in Chile. It's being built now. It should be operational in 3 years. And it's going to...
F1.7, something like that.
It's a very fast optic.
Extremely fast,
Yeah. I don't remember that. You probably know better than I do.
One or something. I think it's
No, it's close to 1, I think.
Look at that secondary obstruction. It's like 60%.
Yeah.
It's going to be amazing. So how do we use machine learning? So first of all, this is one of the earliest uses of machine learning was to try to read what you wrote on your address on your envelope or your package. And there's a nice video. Actually, I've got the YouTube here, but given the hour, I won't show it. But it shows these robots that are working in factories where they're reading labels and then taking packages where they're supposed to go. And they need to be able to tell that, this is a 1 and not a 7. So how do you tell? So this was a problem that was solved with a neural network. Teaching a neural network to recognize numbers. So here's an exercise for the audience. Take out your cell phone. Usually you're told to put your cell phone away. Start up the message app, whatever your message app is. Type a letter and then hit that thing, the automatic fill thing. Just, I don't have my phone with me, so just hit that thing a few times. It's going to write sentences for you. That is artificial intelligence guessing what it is you're going to say. It's not very good. Okay? Right? You're doing it and saying nonsense. Right? It doesn't put together a real sentence. And it also, although I've been using my phone for years and writing lots of messages, even if I wrote a message 5 minutes ago, it doesn't remember that that's the word it should have. It's not very smart artificial intelligence yet. But that's what that is. And more we're going to have that in our daily lives, and, for better and for worse. So we're trying to use it in astronomy. So some jargon. Artificial intelligence is when you're using machines to do things that people maybe find tedious. Machine learning is when the machines can actually learn from the data, and we need to do that for our projects. And neural networks are a specific kind of machine learning. And that's what we've done. My student, Aritra Ghosh, has done this. He basically made a neural net that can look at galaxy images and tell whether they have a disk or they're an elliptical with some probability, say 80% probability. And he uses mathematical manipulations in these networks. He used an actually existing network and then did something called transfer learning. So he took a network that had already been trained to recognize images. Google has spent gazillions dollars, so it can look at images and tell whether there's a person in it, a boat, a bridge, a sky, whatever. And then we said, okay, that's a really useful network. It knows how to find dark and light. It knows how to find sharp edges and smooth edges and all that stuff. And then we just want to teach it galaxies on top of that. That's what we did. So we didn't spend the gazillion dollars that Google invested. We just took what they had for free, thank you, and trained it to do this. And it does it with 80% probability, and it's pretty good. So now we can do the project that Kevin Shawinski did with 1 million people working for years, we can do in a day or two with a neural net. So that's the future. That's what we're going to be doing with LSST. And I think that was my last, I have one more. Yeah, this just shows how you get, each layer finds a different thing. So it might find contrasty type things. It might find a nose or a mouth or an eye. Each layer of the network finds one of those different things, and then it's able to recognize. And that's kind of what we're doing with galaxies. And we need to do much more sophisticated things, because we're not just looking for disk versus round. We'd like to know many other characteristics of the galaxy. Just as if you were going to characterize all the people in this room, you'd have to train a pretty sophisticated neural net. But it's happening, right? You're getting tagged on Facebook because Facebook has figured out who you are. And that's all neural nets. That's not people sitting in a room tagging who you are. So, okay, you can, there's some evil things about machine learning, but at least here it's being used for good. So that's all I was going to say. Thank you very much for coming.
I don't know enough about black holes to even ask an intelligent question, but I'm going to give it a shot.
Do it.
I've read that there's been papers recently, not by quacks, but respected physicists that suggest that black holes actually are portals. And in fact, it helps to eliminate some of the paradoxes with the problems with black holes. I'm just wondering what your thoughts on that.
So these are by real physicists, but they're theorists. and they're using Einstein's theory, to explore, they're exploring what Einstein's theory says. And my attitude is they might be right, but I won't believe a word of it till we make an observation that shows it. You know, there's a lot of theories that are overly simple, and we already know Einstein's theory has got to be wrong in some respect. So the idea is it's the best description of gravity we have at the present moment, but it's not compatible with quantum mechanics, which is the best description we have of atomic, subatomic phenomena at the moment. Those two theories are correct as far as we can see, but they're not compatible. That means there must be some uber theory, or maybe that's not the answer, but one of them could be wrong, or there's some kind of uber theory of which they're a special case, okay? So when people want to explore those theories in great detail, they might, and indeed in quantum mechanics, some of the, I don't know if you're listening about quantum computing, that comes straight out of quantum mechanics. So they do find important things, but I sort of feel like that's not where for me, that's not where the reality lies. Because it may be right, it may be wrong, and no one will believe it until we make some observation that shows that's it. So I have to confess, I don't pay much attention to those papers.
Fair enough.
You know,
Toy models.
they may be real models. They could be real models.
But they,
Yeah. Oh, sorry.
they suggest that, and you just hit on it, that the existence of black holes is not compatible with the laws of relativity and quantum theory as we know it.
Well, it's compatible with it is general relativity, but it's not
That's what
compatible with quantum mechanics, and so there's something we're missing, and let's find out what it
We're
is.
still searching for
In
it.
the field of astrophysics, I really feel we are a data-driven field. There's so many things that were not predicted, not expected, and there's almost nothing where some theorist came out and said, look, the theory says you should see this, go look for it. One great counterexample is the eclipse of 1917, right? The idea that, Einstein's idea that matter would bend light, which was then observed in the eclipse when the position of a star was different, the night before, and then when it had to pass close to the sun. So that's an example where theory made a prediction that was observed and therefore corroborated the theory. But most of the time in modern astrophysics, that just doesn't happen. The discoveries are made at the telescope. So that's where I spend my effort. You were going to ask a question, then we'll go there. Yeah.
The video that you showed where the black holes emit energy.
Yeah, the illustrious video.
Do we have any confirmation that the release of energy is finite or infinite?
Okay. Well, we can certainly observe the radiation from black holes growing, and that's what my group does. So we can. That particular model was a numerical model that's one of the more sophisticated ones that has been done, but the scale they have to operate on is over so many orders of magnitude. They're not doing real accretion in individual objects. They're just saying, in my simulation, when a particle, and the particle for them is something like 10 to the 6 solar masses. It's not a particle the way you and I would think of an atom or something. They just don't have the capacity in their computer. So anyway, they have these particles, and when they get to a certain distance from a black hole, they just say, oh, okay, it's in, and we'll release that energy. It's all, in that sense, fake. It's not, they don't resolve the actual physics. So really what I do, governs what they do. So when I say, here's how much energy we see from black holes, they'll turn around and make sure that's what their models are doing. Like that. Eventually, if our computers get powerful enough, we'll be able to calculate the whole thing out and then do an actual comparison of that theory and our data. But at the moment, they're just doing plausible things and seeing if they sort of look like reality.
So right now you're assuming that energy is just going to keep on coming, it's not going to stop.
It comes out when matter falls in, and matter falling in is episodic. So it is finite. There's not an infinite amount of matter that's falling in. It is finite. The mass of the black hole is finite. But exactly how much energy comes out, and probably more importantly, the thing we really don't know is how does that energy couple to the galaxy? You remember the picture I showed you of Cygnus A with the two thin jets? That's an example of an enormous amount of energy being produced by the black hole, and it's not affecting the galaxy at all. There's these really tiny jets punching through the galaxy and heading out, and almost none of the galaxy is affected at all. So that's a case where the coupling is minimal. But you could imagine that some of this growth of black holes could drive outflows, and we see that in some cases, and those probably have a much bigger effect on the galaxy. So we're still in the early stages of understanding the full range of behavior that can occur, and then figuring out exactly how what is driving it. Is it a pressure? Is it a case of pressure? Is it a case of heating, etc.? We haven't. And then there was a question, from the young man. Yeah.
Answering the first question, you talked about having proof that these things existed, proof some kind of evidence. How would you backdoor the entire escape velocity thing,
So thanks. The escape velocity from a black hole is, of course, the speed of light,
right?
And so nothing escapes from within the black hole, or from the horizon or interior to the horizon. So there's no particles and no light that gets out. But as the material is falling in, it's free to radiate. And that's what we see. We see, as it falls in, it's basically speeding up and heating up, and hot material glows. So we see that, and we also see the effects of energetic particles that are probably accelerated by magnetic fields that are outside the black hole. So everything we see is outside the black hole. There is an experiment to look for the shadow of the black hole at the center of our galaxy using radio telescopes. It's called the Event Horizon Telescope. And they would actually see the absence of light in a certain way. But they're still working on that. They're taking data. They've been taking data for a couple of years, but they haven't yet processed it in a way that they're happy with.
So we can read the effects that a black hole has on its surroundings, but the philosophical paradox of not being able to know what goes on inside still remains.
Yes, and I don't think we'll get past that. Although there are some things I don't understand about it. Like right now, we send vehicles around the moon, which basically determine the interior structure of the moon from its gravity. Okay, so they basically send accelerometers, like your iPhone. It's like sending your iPhone into orbit around the moon, and it's measuring the minute accelerations. They can measure the density of the moon. So why can't we do that with a black hole? I have to say I don't understand that. I've asked a few theorists, but they kind of don't
We
like
can't get an accelerometer there for one.
Well, that's true. That's true, but that's the technical detail. Question here.
How is dark energy or dark matter predicted to interact or not at all with black holes?
Okay, so let me first say a word about what each is. So first of all, the word dark in both those terms, dark matter and dark energy, is astronomer code for we don't know what it is. Dark matter was named that, and kudos to Vera Rubin for having mapped it. It's something that creates attractive gravity but doesn't shine. So it's holding galaxies together. The stars aren't enough to hold them together. And then more recently we've discovered dark energy, which is kind of anti-gravity. It's pushing space apart. And so, and those two things are probably not at all related, except for that word dark, meaning we don't know what it is. How do they interact with black holes? People have asked me this. It's a really good question. Probably there's not a lot of dark matter in black holes. And here's why. Matter, to fall into a black hole, it has to, or to fall into anything, to fall into the sun, it has to lose angular momentum. So if you've taken physics, you know there's angular momentum, which is kind of how much something's rotating. What is it? Okay, if you whirl the thing around your head, right, on a string, right?
Centrifugal force.
Centrifugal force. It's actually centripetal. Yep, that's good. If you try to make it go faster, you have to pull harder. Or another way, if I make the string shorter, like if I make the radius smaller, it goes around faster, right? This isn't the way to say it. Well, it's like tetherball. Does anyone know what tetherball is? Okay. So, if you go around, okay, I'm not saying this well.
The rope gets shorter as it goes around, it goes
Rope gets
faster.
shorter, it goes faster.
Conservation angular momentum.
So if something is not even barely moving and it's far away from the black hole, by the time it gets close to the black hole, it's whizzing around it and it's never going to fall in unless it can lose some of that energy. That's the key thing. So to lose energy, it has to interact with other matter. That's why we think these jets come out, because they're actually the matter that's coming out so that some other matter can go in. With me?
Yeah.
Dark matter doesn't interact with other matter except gravitationally. So it can't lose enough angular momentum to get down into the black hole. So probably, if you let the universe go on for, 10 to the 100 billion years, whatever, 10 to the 100 years, long time, probably black holes would be full of all the normal matter and a little bit of dark matter that just happens to be aimed correctly, right at the center, and then there'll be a lot of dark matter around that can't get into the black holes. So that's what I think is happening. And then the dark energy is just making space expand. So it doesn't really affect gravitationally bound objects like black holes. Good questions. Yeah.
What about the orbits that you showed zipping around the black holes? As they have these big elliptical orbits, wouldn't the dark matter have some impact on that?
Oh, yeah, no. Good question. First of all, those are stars that are going around. They don't even see the dark matter. The only interaction between stars and dark matter is gravitational.
Right.
Gravity is very weak. And so it's not like going through a swimming pool of water. That would be very strong interaction. It's like going through nothing. They don't feel the dark. The dark matter is just like, it's not even there.
But it's keeping the galaxy together.
Gravitationally.
Gravitationally, right?
Yeah,
so the gravitational attraction of that matter, wouldn't that change as it...
That's on a huge scale compared to this movie.
Okay, so that was just the
inner tiniest part.
Okay.
That was the inner arcsecond for you astronomers, right? That's the inner arcsecond of the galaxy.
The entire area occupied by all those stars is like a light year or two or something like that.
Yeah, something like that. It's very small. And there's not much, and the dark matter that's there is uniform, effectively uniform. And so, yeah, it doesn't affect the stars at all. Yeah.
So the theory of the black holes existing in the center of all these galaxies is that they seeded during the formation of the universe.
That's the theory. That's one theory.
Right.
There is another theory, and probably both things are true. There's another theory that you had giant clouds collapsing directly to much bigger black holes. And that probably also happens, though more rarely. And so the biggest black holes we see were probably formed from direct collapse rather than hypernovae.
So it's just like it's just like star formation, but
Yeah.
on a much larger scale with a much bigger cloud.
Yes, and it's trickier. Stars formation happens, you start with a big cloud, but then it fragments into little bits. And the idea is that in the beginning, when you didn't have atoms that were heavier than helium, you didn't have atomic transitions that would cool the gas. If you could keep the gas hot as it falls in, then it wouldn't fragment and form stars. So it's kind of tricky. The theory to do it is kind of tricky. You have to have it be only hydrogen and helium, and also you have to have some really bright ultraviolet sources nearby to keep it ionized. And if you can do that, you can have direct
Really bright ultraviolet source would be a massive early star.
A massive early star would do it. Or a quasar.
One last question, anybody?
Yeah.
I read somewhere that Hawking had theorized that black holes could evaporate.
Yes.
Could you comment on that?
Yes. So we do believe black holes can, in theory, evaporate. The idea is that you have a black hole, and this is the marriage of quantum mechanics and black hole and general relativity. It's very cool, actually. You could so in quantum mechanics, you can have virtual particles created, let's say an electron and a positron pair, as long as they annihilate within a short time that's governed by the uncertainty principle. So Hawking's idea was, well, what if I create a pair like that just outside a black hole, and one of the pair goes in and one doesn't? They can't recombine. So effectively what I've done is I've created a black hole that emits a particle. So that mechanism, as far as we can tell, does happen, and if you did it enough, you could evaporate the black hole. The problem is that in any astronomical black hole, that would only work if you were in a vacuum, if there were no matter to fall in. In any astronomical black hole, there's lots of stuff around, and it's all falling in much, 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 much faster, orders and orders of magnitude faster than they could evaporate. So the place where this was important was when the Large Hadron Collider turned on. whenever that was, 5 years ago, 6, 7, 8, I don't know, time flies. Whenever, people were worried that it would create black holes that would gobble up the Earth and we'd all be gone. Which is, that's a good thing to worry about. But the black holes it would have created, which there's no sign of, by the way, but had it created black holes, they would have been so small, so tiny, that indeed they would have evaporated. The probability is they would have evaporated before any particle could have fallen into them. So they were not a threat for the reason that the Hawking radiation would have killed them off.
Thank you.
Okay, and we should, I think that was a
let's see
sign.
where- So, thank you very much.